One thing the AP exam loves to do for its calculus students is to ask you to calculate definite integrals. And it seems like an odd thing, but depending on the way the question is phrased, there are two very different strategies for solving it, kind of like we've been seeing here. Sometimes we were finding an area, sometimes we were finding an antiderivative. Sometimes we were doing both of them to compare that they're the same, but we might not always be able to do that. So let's take a look at the problems where you're going to use one strategy versus the other to just really drive home which strategy is for which purpose. All right, so right now, this is from page 513 in your notes. So this is jumping a bit ahead. You don't need to make notes of this, or you could just kind of make notes in a piece of scrap paper or in the margins of the current day's notes to help you understand when you would do this. Let's take a look at this first question. What is the value of the definite integral from 0 to 3 of f of x dx? And so here is the graph of the function f of x. And so we don't know the equation of the different parts of the lines. It's clear that these are both straight lines, and this is a semicircle right there in the middle. But off the top of our heads, we don't know the equations for these different curves. And so because we don't know the equation of the parts of the function, finding an antiderivative would be a really unpleasant thing to do. So that is not how we're going to address this problem. We're going to address the problem the way we did at the very beginning of the unit. I am going to draw a vertical line at x equals 0 and one at x equals 3, and the x-axis and the curve itself. And we're going to calculate the area of this shape. So it's a pretty weird shape, but if you break it down into a couple pieces, it's not strange at all. Can you imagine how we can break this down into pieces? Well, I'm going to draw a horizontal line right there and a vertical line right here. And now we've got three different very easy geometric pieces. This is a rectangle, this is a triangle, and this is a quarter of a circle. And so it's very easy to find the area of these three pieces. Let's go ahead and do this. Well, first, what's the area of the rectangle? Well, the rectangle is 2 units wide and 1 unit high, so the area of this is 2. How about the area of this triangle? Well, you can kind of see that it's a half of a 1 by 1 square, so that area would be 1/2, or you can use the formula. This is a base of 1 and a height of 1, so it's 1/2 base times height, 1/2 times 1 times 1. Either way, we get 1/2 for that. And the last piece is this quarter circle. So remember, the area of a circle, remember my rule, cherry pie's delicious, apple pies are too. All right, so the area is pi r squared. What's the radius of this circle? Well, here's the center of the circle, and so going off in this direction or going up, the radius is 2. So the area of the whole circle is pi times 2 squared, which is 4 pi. But we don't have a whole triangle here. We have a 1/4 size wedge. So maybe I'll just draw it like that. Equals 1/4 times 4 pi. So the area of this piece is just pi. So based on that, what is the value of the definite integral from 0 to 3 of f of x dx? Well, it's the sum of these three pieces. So we can write that as 2.5 plus pi. Let's do these next two parts as well. That'll be fun. What is the value of the definite integral from 0 to 4 of f of x dx? Well, once again, we're going to treat this like it's a geometry problem, except this time we're going from 0 to 4. So in addition to that whole shape, we're going to include this shape right here. How is that going to change the area? What's the area of this shape? Well, the area of this triangle is 1/2, just like the other piece, but this is below the x-axis. So we're going to think of that as -1/2. All right, so when we calculate the integral from 0 to 4 of f of x dx, we've got this sum, and then we're taking 1/2 of it back. Or you could think these two triangles are canceling each other out. And so that value is going to be 2 plus pi. And the last question is, what is the value of the definite integral from -3 to +3 of f of x dx? So this is now going from here to here. So now we're including this whole shape as well. Do you think that's going to be a lot of work to figure out? Well, one thing we can notice about this function is that it has vertical symmetry. So it's the same on the left and the right hand side. So we're going to talk about that as we get closer to page 513. But I think you can appreciate the basic argument, which is that this area is going to be the same 2.5 plus pi as the congruent shape on the right hand side, since we have that reflection symmetry there. And so the integral from -3 to +3 is going to be the sum of those two shapes, which we could write as 5 plus 2 pi. All right. So the basic idea that's going on with this problem that I want to make clear to you is that we know some things about the behavior of the function by way of its graph. Since we know the graph of a function, but we don't know a lot of other things about it, in order to calculate the definite integral on that function, we are going to treat it as a geometry problem. We're going to break that area up into smaller geometric pieces that we can calculate the area of, because definite integral is equal to area. All right. In the next video, we're going to see situations where we would not be able to use that because we don't have this information, but we can use the fundamental theorem of calculus in order to solve definite integrals in that situation. So we'll see how that differs.